Hello, my name is Chris Moran. I am a senior cloud architect with a consulting services company in Sydney, Australia. I'm very pleased to present to you the active pedestrian hazard detection system for Innovate FPGA 2019. Start off with this thought. Every year around the world, thousands of people are injured or worse, killed when they are hit by cars because either the driver or the pedestrian, or perhaps both, are too distracted to react in time. It's time that somebody did something about it. And APHD is my solution to that very question. First of all, I want to look at what is the case for autonomous logic. Autonomous logic is the fact that we can't rely on any outside source. We can't rely on the internet. We want to put this into a moving vehicle. It might not always be connected. If it is connected, it might not have high-speed capability. We can't go carrying around hard drives full of model data. The system has to work pretty much in real time. It has to be cost-effective. It must be simple to use. We don't want to be adding additional workload to our drivers. They're already distracted enough. We need to make this very simple. We only want to get their attention when something needs to be done. If we look at a technical overview of the solution, my prototype was built around a 3 gigahertz Intel Celeron CPU with 4 gigabytes of memory and 64 gigabytes of main storage. This is pretty typical of embedded PC class machines, not super fast, but with sufficient storage capability. The system will use 2 or more cameras. In the prototype, they were conventional USB webcams. They could also be video capture devices, and we draw from the onboard cameras which are used for parking in many modern vehicles. In addition, there is a Terasic OpenVINO starter kit which provides the Intel Cyclone 5 FPGA. We are using Ubuntu 16.04 with a 4.13 kernel. The OpenVINO distribution is 2019 release 1, which includes OpenCV version 4. All of the code was written in C++. So why do we want to use an FPGA? It allows us really to move the workload out of the software, out of this relatively lightweight processor, into silicon. It's much simpler from a hardware point of view than embedding a GPU. It integrates nicely with the OpenVINO software libraries via an OpenCL interface, which is well documented public. Benefit of that is that all of our DNN libraries come from one vendor, and that vendor is Intel. So they've got a lot of experience in this kind of thing. It also means that we can use lower price point hardware. As I said, this was built on a Celeron CPU. It's not built on high-powered Xeon machines or even Core i7s and so on. This gives us, in our case, lower thermal demands, lower power requirements. It gives us better performance than we would get normally. Yes, we can get better performance if we went to a faster CPU family, but that becomes not so much cost effective. If we look at the next graph, you can see that the number of frames per second that we could process on its own with the CPU was around about 0.8. Using the embedded GPU, that got us up to 6 frames per second, which is probably adequate for the job. Using an NVIDIA GTX 1080 board, we actually ran this at 87 frames per second. And using the Cyclone FPGA, with no customization to the Intel supplied binaries, we ran at 74 frames per second, which is more than adequate. So the question might be then, well, why would you use an FPGA over using a GPU, other than the fact that this is an FPGA contest? The real reason is looking at moving this into production, and it's around pricing. Now, unfortunately, pricing for GPU devices, very, very hard to get without committing to buying quantities. The only single unit prices I could get on the hardware alone, the NVIDIA GPU was valued at about $1,100 Australian dollars, whereas the Cyclone FPGA is a little over 400. That's a massive difference in price. If we're looking at building this in quantity, the results become quite compelling. We're getting far better bang for our buck. Turning now to look at the architecture diagram, we can see that there are a pair of cameras. The whole thing has been developed around the concept of being able to look for both sides of the road at the same time. We then use standard image capture libraries. Now we're using V4L in this particular case. That will talk to USB cameras, that will talk to various frame grab hardware, just about anything we need. The images are then processed basically through OpenCV libraries, which are linked with the OpenVINO tools. That interfaces to the FPGA device via an OpenCL interface. Once again, all very standard, very straightforward. If we turn to the software overview slide, now the first thing you'll notice is that I appear to have two identical pieces of code. That's not true in a practical sense because it runs as multiple threads, one per camera. But for the purpose of illustrating how the software works, I've drawn it out as though there were two separate stacks. When we start up, we initialize our hardware and our recognition modules. We then throw the software into a relatively tight loop where it captures a frame, passes that to the recognition module to determine if an object matches the model. Now, the objects that we're looking for at this stage are people, animals, cyclists. We could look for other things, but I wanted to keep it nice and simple. If we have a match on one of those objects that we're seeking, that frame will be placed into the motion detect queue and it will then be processed. Otherwise, that frame is discarded. During the development phase, we actually wrote each frame out to disk as a motion JPEG file for later analysis. I will show you some of those. The reason that we don't do this live is that there's no screen to display. There's only a very simple LED display. We don't want to overburden our driver, as I said earlier. We want to keep it nice and simple. So any displays that I show you, the video is purely for debug and testing purposes, and the frame rates are somewhat limited by the write process. The actual processing of the images is occurring much faster than that. Now we're out driving around looking at what the camera is actually seeing, and you can see that it's picking up people. It's identifying them. The vehicle is moving at this stage at around about 55 to 60 kilometers per hour. It's accurately identifying the pedestrians on the side of the road and highlighting them, as we can see. Now we're at a different part of the road, different day, different lighting conditions. Once again, as we see, there we go. We've got some more people. It's grouping them quite nicely there. We occasionally do get a bit of a false positive, but these things will improve as we work on the model. You can see here that people will enter and leave this particular scene. There's another person coming in there now, walking across. Yes, we're actually tracking them quite nicely. More pedestrians. Notice it's not picking up vehicles, trees, lights, etc. It is actually quite accurately identifying what's going on. Some more people into the scene and the system reacts very quickly to them. The vehicle was stationary at this point. What are the results? First, I'm very pleased to say that this system actually does work, and it works in the field. Yes, we've got a long way to go, but as a proof of concept, we've actually delivered what we committed to. We are processing in excess of 10 frames per second using data coming from a moving vehicle, and we are getting prediction within 1 second. So we're actually able to alert the driver within a suitable time that there may be a hazard there. The system is also completely standalone. It does not rely on any input other than the video cameras. There is no user intervention required. One of the things we've learned is that the models are not yet perfect. There's more training required. There's more fine-tuning. The detection and vector tracking still needs a bit of work, but it is functional. Thank you.